Next is the reaction of polyene, which is unconjugated double bonds. So, for example, here in the unconjugated 1,4-DN, so you have two double bonds inside the single molecule, but they are not conjugated. And what happens here is by illuminating a light, so excitation of the double bond make cyclization like this. But this is unstable, and this one of the bond is cut off to make double bond in here and something like this. So that makes a different cyclization of this cyclopropane-like molecules is formed. And then this example is totally same. So it's just the cyclization gives a and since this is unstable, this closing and this bond is off to make and this is also radical, and these are closed to make this molecule. And also some conjugated polyene case, we can think about the reaction process based on the frontier orbital, like constellation. So let's think about that. So here, what we are thinking about is now the conjugated. So double bond. So every 2 steps, you have some double bond, and at the end of this, you have methyl and hydrogen attached at the end, and they are reacting to close this kind of reaction. But the product species are different depending on if this is right induced reaction. It's kind of trans-like structure. On the other hand, some case methyl are on the same side. So why does this happen? It could be explained by the frontier orbital. So first, let's think about check the HOMO and LUMO orbitals. So please draw some sort of the lowest frontier orbital is you have 6 carbon, right? 1, 2, 3, 4, 5, 6. So you can draw like the pi orbital. But of course, the lowest energy must be the same phase, right? And then second lowest one is like this. So one turning point here. And the third one is similarly one. So here the turning point. Like this. And the fourth one will be 1, 2, 3, and 4, like this, right? And I showed you 4 orbitals from the lowest energy because now we are thinking about 3 double bonds, meaning that we have 6 electrons, right? 6 electrons in pi orbital. So meaning that in each of the molecular orbital, you can have 2 electrons. So 1, 2, 3, 4, 5, 6. So this third orbital should be LUMO, right? So lowest on that's a mistake. HOMO, right? This must be HOMO. So highest occupied molecular orbital. And then this one is LUMO. So lowest unoccupied molecular orbital, right? The important thing is in the thermal excitation, right? Thermal excitation, the third orbital, the electrons are occupied in the third orbital. So the reaction starts from this state, right? So if looking at the edge part, they have the same phase of the molecular orbital. On the other hand, if the light is illuminated, so one of the electrons is coming to here, meaning that LUMO is important. And in the case of LUMO, you could see the edge part is now the phase opposite, right? So that's the important things to understand the reaction. For example, here, if this one, this is a case, it's going to closing by rotating opposite for each of the carbon, each of the pi orbitals. And this one is actually mistaken. It's cannot. I'm sorry. This one is, yeah. In this case, right? So in this case, molecule want to react with like this. So rotational direction is same, right? So this is how to make the reaction. And then in this case, what will happen for this is in this case since closing reaction is giving the missile in the same direction, missile on the same side, hydrogen is the same side to make bond. On the other hand, in this type of reaction, missile side is now opposite for the final reaction. So key point to take is in the photo reaction, the LUMO is important, but the summer reaction, HOMO is important because HOMO is only that in the summer reaction, electrons are only in a HOMO, so there's no electron in the LUMO. So the product is dependent on this consideration, right? So you could decide what kind of reaction could happen in the based on this consideration.